So with that, as I said, today we're going to be discussing experimental tests of general relativity. So I will basically just go through them. I will not have time to go through all of the experimental evidence. So in the end, I will tell you about one of the sources I used partially to prepare this lecture, and where you can find a lot more information. Some of it discusses things that we have not seen yet in the course. So that's part of the reason why I won't go through that. But you can find a lot of information in that resource. So the first test, one of the more classical examples of predictions of GR that is not covered by Newtonian mechanics, and you might have heard of it, is the perihelion precession of Mercury. So let's write it down. Perihelion precession of Mercury. So what is this? Well, you know that in classical Newtonian dynamics, if we have a two-body system, for example, then the sun and the planet. So let me try to draw that. So we have the sun and we have a planet, for example, Mercury, that is orbiting this planet, this sun. Then the orbit here is it's an ellipse in Newtonian mechanics. So we have the where the sun is in one of the focal points of this ellipse. So maybe it should be something more like that. And this we have the perihelion and the aphelion, which is these 2 points. And since in Newtonian gravitation, these ellipses are closed. So this means that every lap that this planet makes in this orbit, of course, the eccentricity of this ellipse is slightly exaggerated here. It's much more close to an actual circle. But every orbit it makes, it comes back to the same point. And the precession is that if you go out and observe, for example, Mercury in its orbit, you will see that these points, they move around, so the orbit does not close exactly. So if you do this for Mercury, so the closest planet to the sun, we have a precession which is around 574.1 plus minus 0.65 degrees, arc seconds per century. So, I mean, it's not much, but it's there. And if you look at the Newton, so of course, in reality, we don't have this two-body system. We have other things too influencing the orbit of Mercury. But if you just look at the Newtonian effects, such as the gravitational pull of other planets, the fact that the sun is not really a spherically symmetric object, it has some oblateness to it, which makes the potential differ from the Newtonian point potential. Mainly the orbit of mainly the other planets affect this orbit. That is going to explain around 532 of this. Explained by non-two-body effects. So that leaves around slightly above 40 arc seconds per century to be explained. And so let's look at well, the big surprise is, of course, not that since this is a GR course, we're going to explain this remaining precession by general relativity effect. So what we can do now is that we can look at the Schwarzschild metric. And when we look at the Schwarzschild metric and the motion of a test particle, in this case a test planet, in the Schwarzschild metric, if you remember, we had this space-time. We had this relation that we had with some constant of motion that was E. We had minus r dot squared divided by 2. That should be equal to some potential. And this potential for something massive was 1/2 1 minus the Schwarzschild radius divided by r, and then 1 plus L squared divided by r squared. And we also had that L, this specific angular momentum, was given by r squared phi dot, where phi is the angle in the orbit. So what we can do now is that I'm just going to call this V of r for the moment. If we differentiate all of this, what we will get out is basically that r double dot is going to be well, plus the second derivative of r, that's going to be equal to 0. Or rather, let me do this. So I'm going to do that essentially. No, sorry, it should really be the second derivative. No, so no, I'm getting ahead of myself. Let's do the following. Let's say that V of r is basically some constant V of r 0 plus V double prime of r 0 r minus r 0 squared, and then there is a 1/2, right? So then we do have this plus higher order terms in r minus r 0, and r 0 here is a minimum of V of r. So if we expand this potential around the minimum, we get this. So what we get now, if we insert this potential here and we differentiate, is that r double dot plus v bis of r 0 r is equal to 0. So I'm just going to call this second derivative k because it's going to, or let me call it k squared because it's going to be simpler to write. You recognize this as something that has harmonic solutions. This would mean that r would be equal to, or rather, r minus r 0. So I've forgotten r 0. So r would be r 0 plus something that is a cosine k tau plus some phi 0, some constant there. So what we get is an harmonic oscillator essentially around in the r coordinates with a period that's given by this k. So that this period is directly given by this second derivative of the potential. So the period in r, if we write that out, that's going to be essentially 2 pi divided by k. So that's the period in r. What we can do now is that we can compare this. If we have an approximately circular orbit, for an approximately circular orbit, then we have that R in this equation is approximately, we can approximate that by the constant R0. So that means that we would have L equals to R0 squared phi dot, which is just R0 squared d phi d tau, right? And now everything apart from this d phi d tau is constant, so we can integrate this. So we obtain the following. We obtain that delta phi during this time, tr, that's going to be given by L over, or sorry, L squared, right? No, L over R0 squared, 2 pi divided by K. So this is the expression that we have now for the change in the phi coordinates over the course of a full oscillation in the r coordinates. So for example, if I start here at the lowest r coordinate and I follow this path around, the question is, what is the difference here in the angle between the closest point of one lap and the closest point of the next lap? So I'm not going to go through the exact maths here because it becomes rather involved. Instead, I'm just going to say that it's what's relatively easy to do is to make an expansion in the Schwarzschild radius here. And if you do that, so expanding in essentially the Schwarzschild radius divided by L, what you're going to find is that delta phi is going to be approximately 2 pi times 1 plus 3 Schwarzschild radii divided by 2r0. So if we write down the Schwarzschild radius in terms of the mass of the sun in this case, this would be 2 pi 1 plus 3 gm divided by r. Now, what you'll see is that if everything had been Newtonian, then I would not have had this term with a Schwarzschild radius in it. No, sorry, I would not have had this term with L in it. But now I do, which leads to this term appearing. No, I would not have had this term essentially, sorry. And I would have been able to neglect some other terms. But the point is, in the Newtonian case, this was exactly 2 pi because the orbit closed. Now instead, for every orbit that you make, you have an additional angle, which is so delta phi minus 2 pi. That's the additional angle that you make every period in R. That's 2 pi times 3 rs divided by 2r0. So just inserting now for Mercury. So what we have for the Mercury Sun system. So for the Sun, we have a Schwarzschild radius, which is around 3 kilometers. And the orbit for Mercury's orbit, we have that R0 is approximately 5.8 times 10 to the 7 kilometers. So indeed, Rs divided by R0 in this case is going to be very small. So this is going to be a relatively good approximation. And what we had before was what we discussed here. It was the angle that these points move around per century. So in order to get century, we need to know what Mercury's orbital period is. And it's 88 days. So then we can get the number of periods per century, which means that we can then multiply this number, which is the number of which is the change in the angle per orbit, by the number of orbits in 1 century. So this gives us that in 1 century, the GR effect is approximately 41 seconds of an arc per century. And if you do a more careful analysis, you will find that it's approximately 42, which was exactly the difference between the Newtonian predicted result and the observed result. So the GR effects indeed accurately describes this discrepancy between the Newtonian result and the observed result. So the second classical test of GR, you might have heard of this. In 1919, there was a solar eclipse that became very publicized in the media of that time. And that was because Eddington made an experiment during this solar eclipse. This has to do with the gravitational bending of light. So the bending of light. Now, we have discussed in the course already how much light deviates in a weak gravitational point. I mean, the potential from in the Schwarzschild metric, essentially, in the weak field limit. So the point here is to have your sum, which provides you with this gravitational potential, and then you take a light signal and you take a star which is far away, you let it pass by close to the sun. It should be at least something like that. So, and here you are at Earth observing this. So you will see the light coming from essentially that direction, right? So you will think that this, well, it will appear to you as if the star is over there instead of being over here in this direction instead. Now, of course, you know what the sky looks like normally. So you know where this star should be, which means that if you look at it when it's close to the sun, you can compute the angle that the star makes to where it a priori should be in the sky. Now, the reason, of course, that Eddington performed his experiment during a solar eclipse was that you should not look directly at the sun when the sun is shining. I mean, the sunlight would typically drown out all of the starlight from this star behind. So even if you use instrumentation, you should not look at the sun directly. But if the moon provides an effective like screen towards the sun, then you can look at the stars behind. So the idea here is that, well, we discussed this bending of the light in one of the lectures already. So what we found was that if this distance is b, so the closest approach distance essentially, then the GR prediction was that this angle alpha should be given by well, approximately 4 GM divided by b. So b here is the distance from the center of the sun to the closest approach of the light to the sun. So, but the question is, can you make a similar prediction in Newtonian physics? And the answer is yes. Also in Newtonian physics, you can imagine that the light would bend. And the reason for that is, well, it's not a priori clear in Newtonian physics what should happen to light, because if it's a wave, it should just propagate. But if you consider it as a particle, you can actually come up with some sort of prediction for it. So what you know that is in Newtonian physics. So I'm just going to consider here a particle coming in from this direction at high speed and passes by the sun and ends up on the other side. And I'm going to compute essentially what is the deflection here. So in Newtonian physics, if the sun was not there, the particle would, of course, just go on at essentially the speed of light, and it would just pass by. So I'm going to compute the, just as I did in the GR case, I'm going to compute the deflection angle by computing the velocity now induced orthogonal to the original direction of motion. So I'm going to take something like this. So I have the gravitating body there. I move along like this. And so if this is r, I'm going to use this x coordinate. So the acceleration now in the y direction, which is what I'm going to be interested in. So the acceleration perpendicular to the direction of motion, that's going to be approximately equal to the gravitational acceleration, which is mg over r squared. But then I only want the component in the y direction here. So that component is going to be, I use the same b over r. So that's the appropriate trigonometric function. So this all in all is mgb divided by r to the third power. And if I integrate this along all of this line, then I get the difference in orthogonal velocity to be the integral from minus infinity to infinity. Again, I'm assuming that both the star and the observer are at infinity, of gmb divided by the square root of b squared plus x squared to the third power, and then dx, because I'm assuming that the speed of light is 1 here. And if I do this, and I perform this integral, I get 2 gm divided by b, which is the GR prediction divided by 2. So you could argue that there should be this this difference, or you should get a deflection also in the Newtonian case. However, that deflection is half of the deflection that's predicted by GR. So what you do, you go out and measure it and see if it's the full amount or whether it's half of that amount. And there was a lot of controversy, in particular regarding the precision that Eddington had in his experiments. But modern reanalysis of his data showed that he was probably right to draw the conclusion that general relativity was indeed the correct result. However, I mean, this has been repeated, and I think it was in the 1960s that, I mean, it was conclusively shown in radio wave frequencies that indeed it is the general relativistic result that is the correct one, which again then is an experimental evidence for general relativity as compared to Newtonian gravity. So the next experimental test that I wanted to discuss is what is called Shapiro delay. So this is nothing that I think I skipped this in the lectures when we were discussing weak gravitational fields. So let me just briefly discuss the theory behind. So the idea here is that if we are essentially in a weak field limit, then we can then we know that light travels essentially along straight lines with some small deflections. However, we can compute then how long will it take us to send a light signal somewhere and then have that light signal bounce back and come back to us, and we can compare that to how long that would have taken if the light did not travel through this gravitational potential. So if you remember when we discussed how light rays moved in a gravitational potential in the weak field limit. So in the weak field limit, we had the following. So I mean, the basic idea here is to put the s squared equal to 0. So that is in the weak field, it's 1 plus 2 phi dt squared minus 1 minus 2 phi dx squared, where phi here is the gravitational potential. So this means that if I use some parameters, some affine parameterization here, that what I will get for the for such a light signal, it's that 1 plus 2 phi t dot squared has to be equal to 1 minus 2 phi and then x dot squared. And the absolute value of x here is the standard Euclidean distance, so it's the coordinate distance essentially. However, if we here solve for the absolute value of x dot divided by the derivative of the coordinate time with respect to this parameter, then we find that this is given by the square root of 1 plus 2 phi, which comes from this, of course, and then divided by 1 minus 2 phi. And as long as we're in the weak field limit, we can make an expansion in phi. So this is approximately equal to 2 phi, 1 plus 2 phi. So this is actually now equal to the change in the coordinate distance per change in coordinate time. That's just by the chain rule. So let me actually insert this here. Oops, I lost the derivative. So I mean, just by the chain rule, this would be this multiplied by this, which is just exactly this ratio here. So this is the change in coordinate distance per coordinate time. And as long as we're stationary in this space-time, our coordinate time is going to be proportional to our proper time for us as observers. So this means that if the light now travels through a gravitational potential, and remember now that the gravitational potential is typically negative. So for a point particle, it would be this minus 2gm over, minus mg over r, right? This is the typical Newtonian point particle potential. So phi here is negative. So that means that this is smaller than 1, which means that the distance, the coordinate distance traveled per coordinate time is going to be smaller than the speed of light, because we have 1 minus something, which is then smaller than 1. So the coordinate distance covered per coordinate time is smaller than the speed of light. So that means that in terms of coordinate time, if you travel through this gravitational well, it's going to take a longer coordinate time to travel back and forth. And since the coordinate time in this space-time is proportional to our time as observers, we're going to expect that it takes longer for us to receive this signal back. And you can test this. So the way to test this is basically to have the following setup. You need a large gravitating body. So something like this. I'm exaggerating here, of course. This is not going to be to scale. And then you have some planetary body here. So this can be something like Mercury or Venus. And we are over here on Earth. So say Mercury or Venus. And the point here is, of course, that we want our signal to go as close to the sun as possible without actually hitting the sun. So we send a radar signal to this planet on the other side of the sun, that then bounces back to us, and we measure the round trip time. So measure round trip time. So you know what this time would be if it was not for the Shapiro delay, and you can compare with that. So I have, let's see, where did that go? Yeah, so this is essentially the setup. So this figure here is actual experimental results from Shapiro in 1968, and it's Earth Mercury. So and I mean, you see the delays are like microseconds. So this is the additional delay from the Shapiro effect, and you see that this is positive. And what is happening here, of course, is that these are conjunctions. So it's essentially where you have Mercury behind the sun. So what you see is that it goes up as this planet or Mercury moves closer to the sun, and then when it comes out on the other side, it goes down again. So that the closer you are, the more effect you have, of course, of the Shapiro effect. And it matches pretty well to the prediction of GR. Of course, you can make this more accurate nowadays as well. But that's the basic idea behind the Shapiro delay. Any questions on that? Okay. So the next thing I'll discuss, so another test of GR that succeeds, is the so-called Pound-Rebka experiment. Oops. And this is a measurement of gravitational redshift. So a priori, what you have, if you have an atom that is emitting some wavelength, so let's say that we have an excited atom here, and you have this excited atom emitting some photon. What you generally would end up with is the following. So the atom de-excites, and you send out a photon of some wavelength gamma. But generally, I mean, we are looking for very small effects here, because we're going to see, what they were looking at is like gravitational redshift in tens of meters of vertical distance. So one effect that we in general should have to take into account is the recoil of the emitting ions. So what they did now was to use the so-called Mössbauer effect. So what you do is that you don't take just an ion like this. You take a Mössbauer effect is that you take an ion or take ions in a what is the word it was in English? Jitter in Swedish. So essentially you take ions that are placed in a grid like this. So as long as that is true and you have your excited ions being essentially trapped in the grid, this recoil is not caught just by the ion itself, but it's caught by the entire material. And since the entire material is much heavier than each individual ion, you get a much better grasp of, or rather you reduce the recoil energy, which means that this gamma is going to be much closer to the actual transition energy. So what you do then is that you take your atom. In the case of the Pound-Rebka experiment, these were iron ions placed in this grid for the Mössbauer effect, and you place your detector up here, and you look at what frequency these gammas will have. So you place them in a gravitational field, and you place them at the height h here. Now, if you remember when we discussed gravitational radiation, essentially, when we discussed gravitational time dilation, gravitational redshift, what was important here was essentially the square root of GTT. So we had the GTT at point A divided by the GTT at the second point. Now, in the weak field limit, this is essentially the square root of 1 plus 2 phi A divided by 1 plus 2 phi B. So if we make the series expansion here, this is approximately phi A minus phi B. So it's the difference of the gravitational potentials at these points. And as long as we have this approximately constant gravitational field, the difference here is going to be proportional to the gravitational field multiplied by the height difference. So that's the difference in gravitational potential. It's going to be approximately equal to GH. And if you want to insert the speed of light again to get the correct units, it's GH over c squared. So if you look at what was going on in the Pound-Rebka experiment, H here was around 23 meters. And G, you know that this on the Earth is around 9.8 meters per second squared. So the actual effect here, there is something missing here. I should insert a 1, of course. The series expansion, 1 plus. But this GH is the difference of the potentials. So the point here is that if you look at the redshift, which is essentially going to be proportional to this GH over c squared, the redshift is going to be, if you just insert these values, you have 10 and you have something 10. What you get in the end is a Z, which is somewhere around 5 times 10 to the minus 15. So that's the relative shift in in the light frequency, essentially. So what you will do is that you will observe a redshift, so a smaller frequency up here than you had up here. And of course, you can also reverse this experiment. You can put your atom up here, and you can take your detector and put it down here. And then you send this light signal down, or you have these photons going down instead and being observed in the lower detector, and then of course instead you will observe a blue shift. And the observation here was, let's see, I wrote that down, so it was the observation was 5.13 plus minus 0.51 times 10 to the minus 15 versus the prediction, which is 4.99 plus minus 0.51 times 10 to the minus 15. So indeed, again, we are, I mean, just looking at this, we observe that the GR prediction for the gravitational redshift is correct. But in order to get this kind of precision, you really had to exclude this recoil of the atoms using the mass power effect. Well, I mean, speaking of gravitational redshift, of course, you can do similar things with larger gravitating bodies. So, for example, if you look at stars, you can look at the spectral lines of stars. So this is also gravitational redshift. Gravitational redshift of stellar spectra. So a priori, if you have a star, something like that, and that star emits light, the thing you know here is, I mean, you know how light in the stars are created thermally. So you have absorption lines in the spectra. So you have some frequency spectra, and you have some intensity, and basically you have this black body radiation, apart from the fact that you have some absorption lines in that spectrum, depending on the elements that are present in the stellar atmosphere. So you can go and look at where are those lines located. It's just that if this star, I mean, this star is massive, so essentially outside everything is going to be described by the Schwarzschild metric. So that means that you're going to have gravitational redshift of this photon, which is here emitted, or rather this absorption line is here going to be at the absorption frequency that you would expect from that particular element. But what's going to happen instead is that that is going to get redshifted. So what you're going to observe is a redshift of this entire spectrum. So you're going to shift it towards smaller no, that's not the redshift. Redshift is towards larger frequencies. So all of this, well, the entire black body spectrum, but a priori, I mean, then you would have to know the temperature of the star on the surface and so on, but also the absorption lines are going to be redshifted. So by this shift, you can tell what is the difference in gravitational potential at the surface of that star and at infinity, where you are here looking at that star. So that's another way of actually determining that there is gravitational redshift going on here. And this can be observed. Any questions on gravitational redshift in general? Okay, so I mean, we already talked about gravitational waves, I think, in lecture 9, but let me mention a few more things. I mean, we now have actual observation of gravitational waves, and that is basically what we discussed in lecture 9. But even before that, so even before we had this actual observation of gravitational waves, there were indications that gravitational waves were actually being emitted. So, for example, you could look at binary pulsar systems. And if you do that, let me take that from here actually. So let me copy this. Copy and paste. So what we see here, what we see here is over time, we have this binary pulsar, PSRB 1913 plus 16. And that's a binary pulsar, so it's a binary system that's revolving, and you can measure its revolution time essentially. And what you can see here is the cumulative shift in seconds measured over this time interval. So, I mean, of course, you start at 0 difference because this is where you start, and then you can see that as time goes on, and we keep measuring this pulsar, you see that the period goes down, and this is essentially because the gravitational waves sent out between those, due to this binary system orbiting each other, leads to essentially energy being expended in the form of gravitational waves, and so the pulsar comes, the system comes closer and closer together, and because of conservation of angular momentum, increases its frequency, and therefore shift downwards in the period. And eventually, this will lead to a gravitational merger. And these are the kinds of events that you would observe in terms of, or stand a chance of observing in terms of gravitational radiation, as we discussed. The LIGO observation, the first real observation of gravitational waves, was due to the merger of two black holes. That was also one of those binary systems spiraling towards each other. Of course, you could not see the black holes before, but you could see the gravitational waves coming out of that in the end, before the merger occurred. And as you can see from this figure, I mean, there are the experimental points, and then you have the prediction from general relativity. And this is the prediction that is made by assuming that gravitational waves are being sent out at the rate predicted by GR. Any questions on gravitational waves? We discussed this already in lecture 9, as I said. Okay, I don't want to go into too much detail in too many things here. So I'm just going to mention a couple of other things. There's, of course, more gravitational lensing effects. You can study gravitational lensing in the strong regime. So I'm just going to mention other effects, other important effects. You have strong gravitational lensing. Just as an example of that, you can have, I think we discussed this briefly if you have something very heavy that's in front of your object that you want to study, which is there, and we are over here wanting to study it, essentially, if it's very heavy, you can get several possible paths, and if it's right behind the object, you can end up with what is called an Einstein ring. So essentially what you would see here, if I put something like a screen here where I project what I would see on that screen, essentially it would be something like this. You have the heavy object in the middle, and then you have maybe, if it's not spherically symmetric, you have maybe several images like this, essentially gathering up in a ring like this around the object. So all of these images of this object behind, they are the same object. It's just that due to this gravitational pull of this heavy object that is lensing it, you end up with this, and it's called an Einstein ring. So that's a strong gravitational effect. There is also something called microlensing, which is essentially if you look at at very far galaxies, and you have many weak things going on in between, a priori, you don't know how the galaxies in the background look like, because they are all elongated like this. And you don't know exactly how you're seeing them, but you can kind of know how this should be statistically distributed. So if you look at like a statistical sample of galaxies, you can kind of infer how they are you can infer the mass distribution in front of that by looking at the statistical properties of the galaxies in the background. So such that, are they stretched out in this direction and pushed together in that direction, or how does it look? So that's microlensing. We also have things like gyroscopic effects. So you might have heard of several satellite experiments. So what is going on is essentially that you can take a satellite, you send it into orbit, and you put a gyroscope in it, or several gyroscopes in it. And then you look at, over the course of the revolutions, how does this gyroscope change these gyroscopes, how do they change their orientation? And that then has to do with parallel transport of this gyroscope. Since it's in free fall, you have to parallel transport not only the forward velocity, but also the spatial directions of this gyroscope. You parallel transport it around this orbit, and you see how it should be. And these measurements also agree with the predictions of general relativity. There's something called the frame dragging, and that's something that we have not discussed. It's essentially an effect that you have not in a shorted space-time, but in a space-time that a rotating black hole would describe. Can you have a dragging of the spatial frame around the black hole? So I mean, I'm not going to discuss it in much detail, just mention it so that you know that these kinds of effects exist. And then of course we have all of the cosmological evidence of general relativity as well, such as the fact that if we look back in time, the standard Big Bang theory with the standard cosmological theory is very compatible with what we can observe. For example, that the background temperature of the cosmic microwave background today is around 2.7 Kelvin, right? And if you compute at what temperature it should have had when it was released, you end up with something like 3000 kelvins. And this is then compatible with things such as cosmological redshift that we discussed, I think, last time. Other things that you can do, it was in recent news, I think it was even last year, we had the results of the Event Horizon Telescope. Yes, April 10, 2019, came this press release. So this is the first actual, well, image of a black hole. So this is the supermassive black hole at the center of, I don't know if you see this or if it's too small. The galaxy is M87. That has a supermassive black hole in its center. And this is then the first image taken of a black hole. So what you see here is essentially the central black disk, and it's surrounded here by an accretion disk that's emitting a lot of gamma rays, essentially. As the matter in this accretion disk becomes very hot, you can compare now, well, first of all, the size of the black hole to its predicted mass. So you can compare the optical size of the black hole to what you would expect from GR, and that matches. And you can also kind of observe the accretion disk and infer what you would expect from an accretion disk from general relativistic effects. And that also matches. There are many other tests that you can do as well. I am not very familiar with all of the tests that you can make just from these pictures, but this again, this observation from last year was also very much in favor of general relativity. I don't think that anyone actually doubted that general relativity would be giving a better description than Newtonian physics here, but you could always imagine that there is something else going on, some sort of physics that we don't know about. When we discussed what action we should have, I mean, I just put the Einstein-Hilbert action there, just putting the Ritchie scalar essentially as the Lagrange density. You could imagine having other possible additions to that, but all of the observations that were made here of this black hole, and also the gravitational waves that were recently discovered by LIGO, all of these are so far compatible with general relativity.